So Ken told me in the interest of time, go on stage, introduce yourself. So here I am. My name is Jacopo Buongiorno. I'm a professor in the Department of Nuclear Science and Engineering here at MIT. And today I want to tell you about the marriage of two technologies, nuclear batteries and advanced industrial production, which can potentially transform the way in which we produce, consume energy, as well as run our economy. But first, a big step back, and let's look at the big picture. If I were to run a survey in this room about what are the three most compelling challenges that we're facing as humankind, I'm pretty sure a vast majority would agree that it's what I put on this slide. So we are facing a crisis in climate change, both the mitigation and adaptation sides of it. We're facing major geopolitical instability and economic inequality. And the key to the solution of all these challenges is energy. Access to energy, abundant energy, can diffuse competition for resources and therefore diffuse geopolitical instability. The use of clean energy is going to displace a lot of emissions, which help obviously with climate change. And then access to energy or obviously also help with providing economic opportunities. So if you look at the history of the energy generation and use and go all the way back to, say, Roman times in my native country of Italy, the energy sources, in this case a water mill, and the energy users, in this case the production of flour and olive oil, were always co-located. That has always been the economically most efficient way to run production activities. Fast forward 1900 years, and at the dawn of the Industrial Revolution, you see a similar phenomenon still. The emergence of clusters of production activities and therefore cities that go with it are along water streams because of the access to hydropower. The problem with this traditional approach is that the energy resources were very constrained because you were basically forced to be next to a water stream. So in a way, you could look at the history of the past 200 years as far as energy is concerned as the evolution of a system that has become more interconnected and larger to basically access energy everywhere and anywhere and then use it elsewhere. The problem with this new approach is that you have energy generation and energy users that are geographically separated and static. They require massive transmission infrastructure. For the electric grid is transmission lines. For hydrocarbons is pipelines. Very high capital intensive equipment has low utilization factor because of high variability both in demand and intermittency in supply. If you think about the average utilization, for example, for solar and wind, or the backup that goes with it is usually pretty low. And then last but not least, these complex interconnected systems are almost inherently vulnerable to external perturbations. This could be either extreme events, and for example, here we get the occasional polar vortex which takes out the grid for a couple of days, or malicious attacks of terrorism or even war. So what is the solution? Well, I would propose that the solution is a dense and clean energy source coupled with modular industrial systems, and I'll tell you what those are in a minute, that are co-located but universally applicable. And therefore, you realize a system that is distributed but not interconnected. So it doesn't have the vulnerabilities that I just described. Okay, so there are sort of two players in this drama that I'm going to introduce one at a time. The first is the energy source with the right features, and that's what we call a nuclear battery. So what is a nuclear battery? Well, it's a small nuclear reactor, microreactor, let's say producing between 1 and 20 megawatts of heat and or electricity. If you're even vaguely familiar with traditional nuclear power, they tend to be much larger plants of the order of a gigawatt, and they tend to be connected to the grid. This is different. It is still carbon-free because that's the nature of nuclear. It does not require water for cooling, so again, it decouples you from proximity to bodies of water. It is a fully standardized reactor or system design. It is expected to be mass-produced in factories. Factories are high productivity environments as opposed to construction sites, which are typically lower productivity environments. It is transportable, as you can see in the image here, in 2 or 3, depending on the design, standard containers. And so it's literally has the potential to be a plug-and-play energy source. It could take of the order of days to weeks from the time these machines arrive to the site to the time the customers or the users actually start to get the energy that they need. For economic reasons, you cannot afford to have large cadre of operators on site, so they're being designed to be autonomous or semi-autonomous with remote monitoring, not necessarily remote control because of cybersecurity issues. And then interestingly, this being nuclear reactors, their energy density is very high. They can provide that energy and or electricity for say 5 to 10 years, again it depends on the design and the use case, without any refueling. At the end of that period, you do need to refuel them, and here comes the next sort of innovation. Instead of refueling them on site, you ship this nuclear battery to a central facility where it's opened up, defueled, refueled, refurbished, and then either sent back to the same site or sent to a different site. And part of the reasons why we call these batteries is because what we have in mind is AA, AAA, D batteries, which are all interchangeable. The customer doesn't care if you're getting unit A, B, or C, as long as it's compatible with their energy use there, it works. An implication of this off-site refueling is that there is no need for handling and storing radioactive material at the site. And again, this is certainly good for social acceptance. Nuclear energy tends to be very, very dense. And so here you see, or maybe you can't see, that little green rectangle on this slide is roughly the size of a 10 megawatt nuclear battery. And that's how it would compare to a nominal 10 megawatt either solar field or wind turbines. And then last but not least, there is a lot of excitement in the West, in particular in the United States, because unlike the larger plants for which sort of the center of gravity or the industry has really shifted towards East Asia, US suppliers are in the lead. So you might be familiar with some of these companies, Westinghouse, BWXT, X-Energy, et cetera. So that's the first technology. The second key technology that enables this potential transformation of the economy is what we call advanced industrial production. And so any process or production technology that can be miniaturized, modularized, and mobilized is what we refer to here as advanced industrial production. It allows for deployment in increments, and I will show you in a couple of slides what that does in terms of cash flow and economic viability. And once again, it has the potential to basically be a plug-and-play approach. Some examples are shown here with their more traditional, more monolithic counterparts. So the first one on the left there is a data center. The one on the very left is a traditional mega data centers. It might require hundreds of megawatts. It takes several years to build, and it costs several $100 million. And what you have immediately to the right of it is a modularized, containerized, and mobilized data centers, which of course does not have the same power, so you need to sort of stack them up and deploy them in increments. But it also requires a lot less energy to run, and it can be deployed quicker. Other examples that you see here are pharmaceutical facilities. Even agriculture can be containerized. It requires a lot of energy, again, so you need an energy source there. And then hydrogen, which is very important for basically decarbonizing the transportation system. So when you put these two technologies together, nuclear battery plus advanced industrial production, you have what I would call a potential game changer. The concept is shown here for a completely hypothetical site. We focus on states that are particularly suffering during this energy transition because they were heavily based on hydrocarbons, and now they're sort of losing that economic power. So this could be, for example, a site in Wyoming. There are a lot of mining sites, so you have access to raw materials. The idea here is to deploy one or more of these nuclear batteries at that site. And what do you do with it? Well, nuclear batteries produces electricity and heat, and you can use both sort of energy streams for useful things. With electricity, you can actually do electric mining, which would decarbonize the mining operation themselves. And with both heat and electricity, in this case, if you have an iron mine and you produce iron ore, you can actually produce steel with new processes like the molten oxide electrolysis and the direct current sintering. And so what you have now is a truly carbon-free steel in some form. It could be rods, it could be plates, but you don't stop there. You can co-locate at that site also manufacturing and assembly facilities, which would also be powered by the nuclear batteries. And then what you get at the other end of this process is the finished product. And so, as I'll show you in the next slide, the economic proposition or the economic value of that finished product is much higher than if you were to sell commodity steel to the market. The features of these systems are that you don't need grid or pipeline infrastructures. You have shortened markup chains because basically you have fewer middlemen that you have to pay along the process of going from raw material to finished product. It allows for incremental provisioning. I'll define what that means in the next slide, and I'll show you what it does, as I said, in terms of economic value. And finally, you can say with a straight face that the finished products coming out of this system are carbon-free because the whole system is powered by a carbon-free energy source. Okay, so this business of co-location and incremental provisioning, what do we mean by that? Well, we mean what I just described, that you co-locate energy source with advanced modular or advanced industrial production. But further, it also means that you do that in smaller increments. So instead of spending a lot of words here, let me show you this plot. So there are three curves here. The top curve shows a nominal loading factor for a particular alloy of steel. In this case, actually, just to prove the point, we pick something that is essentially a commodity. And so the margins in principle would not be particularly high. This sells for about $800 per ton. So that top curve, the gray curve, shows a ramp up, then steady, then there is maybe some economic crisis, so the demand softens a little bit, and then you go back up again. And then the other two curves compare the cash flow for the two approaches that I described. One, this co-location of nuclear batteries with advanced modular production. And then the other one, the more traditional, where you deploy a larger plant up front, anticipating a certain capacity or a certain demand over the course of the years, and then try to recover that investment over the years. And so the other, on the x-axis here, I forgot to say, but what you have here is time, okay, in years. So focus first on the orange curve, which is at the bottom. Not surprisingly, you have a big investment up front, and so your cash flow becomes negative very quickly. So you're accumulating debt, essentially. Then you start to make stuff and selling it to the market, so it goes up a little bit. But there is that dip in demand because some economic crisis has occurred, and so you go down again. And then finally, if the demand is stable, you go up and you reemerge and become cash positive after 14, 15 years, actually. I can't really, 15 or 16 years. Now, compare that to blue, which is the approach that we are advocating for. And basically, you can see that the cash flow is always positive. Now, in reality, if I were to zoom on year one of that project, you would see that at the very first few months, it would go negative because, of course, you need to put up some capital at the very beginning, even for that smaller system. So needless to say, this is quite attractive from an economic point of view. I just shown you that example with iron and finished steel products, but literally, you could apply this trick or you could play this trick in every sector of the economy. And the timeline that you see there on the right simply indicates what applications, in our judgment, are gonna go first, because either your competition is very expensive, or there is a compelling need for this new approach that the traditional approach doesn't satisfy. So things like military bases, microgrids, we just talked about mining sites, indoor aquaculture, farming, data centers, and the list goes on. You could do district heating, you could do flood protection, running pumps for coastal communities. A little bit more futuristic, you could power space bases, even provide propulsion to ships. E-vehicle charging stations, biofuels. Here you're starting to get into more commodity-like markets, and therefore probably it's not where you want to start. You're going to go there a little bit later. Why is this important? Well, if you're strictly thinking about climate change and displacing emissions, there is a disproportionate amount of interest at the moment in decarbonizing the grid. Well, guess what? The grid, once it's perfectly decarbonized, it's only 25% of the emissions. Now, I'm perfectly aware a lot of people think that we can electrify the hell out of everything, but a lot of sectors cannot be electrified. It's never going to be either feasible technically or economically attractive. And so this is the value proposition here. You could actually apply this approach across every sector of the economy. So I'm going to leave you with this quote. The challenges are massive, but I love this quote. This is very optimistic. So, you know, your future has not been written yet. No one's has. Your future is whatever you make it, so make it a good one. And you probably recognize this is not a philosopher or a writer, but it's dear old Doc Brown from Back to the Future, which brings me back to my childhood. So with that, I guess we're on to the next speaker. So.